are all around us. They are involved in most aspects of our lives. Let's see a few examples. Yugandhar is 4 feet tall. He is 11 years old. His weight is 33 kilograms. Note that these numbers are increasing. Let's look at some more examples involving numbers. Did you know that an average pomegranate has around 600 seeds? Mount Everest, Earth's highest mountain peak, is 8,848 meters tall. The length of the equator is around 40,075 kilometers. The distance between the Earth and the Moon is 3,84,400 kilometers. As you can see, the numbers are becoming greater with each example. Can this pattern end? No, there is no end to the ascending order of numbers. All numbers can be shown like this on the number line. We start counting from 1 if there is at least one object. When there are 0 objects, there is nothing to count. So all numbers, 1 onwards, are called counting numbers. And these counting numbers are called natural numbers. They are also known as positive integers. Natural numbers are denoted like this. We add 0 to the counting numbers to make subtraction possible. When we subtract any number from itself, the result is always 0. When 0 is added to the set of counting numbers, they are called whole numbers. Whole numbers are denoted like this. If we go below 0, we get negative numbers. So, the other name for whole numbers is non-negative integers. Thus, the set of whole numbers is nothing but the set of natural numbers with 0 included.
Meet Max, the smart little frog. Max is very hungry today. He spots a juicy little worm on lily pad 8. Max is all excited and he can't wait to get there. It will be fun to see Max get to lily pad 8. All right, let's begin. Max is on lily pad 0 and needs to move to the right to get to lily pad 8. Max adds the number 8 to 0. Let's check if he can get there. He did! Did you see how smartly Max took 8 jumps to the right to reach lily pad 8? Look how happy he is to taste the juicy little worm. That was a tasty bite. But wait! A nice little dragonfly has landed on lily pad 3. Max wants to eat that too. Now, how should he get to lily pad 3? Any ideas? To get to lily pad 3, Max would need to move to the left. Shall we subtract 5 and check if he can get to that lily pad? Max hops 5 places to the left and lands on lily pad 3. That was delicious. Max is happy. Hey, he's just spotted his friend Croak on Lilypad 0. Max really wants to meet him. How do you think Max will reach Lilypad 0? Let's check if he can get there by subtracting 3 from 3. Max and Croak are very happy to meet each other. Max is excited about his hopping skills and wants to use them to impress his friend.
Look, Croak, he yells. Watch me leap to Lilypad 6.
You will notice that Max is jumping 2 lily pads at a time, instead of taking them one by one. This way, he can reach Lilypad 6 quickly. Aha! My lily pads have transformed into a number line for whole numbers. Whole numbers, by the way, refer to the collection of all the counting numbers along with 0. Observe how this number line begins with 0 and progresses to the right. Each whole number is marked as a point. The distance between any two consecutive points on this number line is equal and is called unit distance. Now, let's learn how to carry out addition, subtraction and multiplication on this number line. Let's begin with addition. You will learn to add the numbers 5 and 4 on the number line. I will jump 4 places to the right from 5 on the number line. I reach here at 9. This means that when you add numbers 5 and 4, the total is 9. Next, let's look at subtraction on the number line. Let's take an example. Can you guess how we could subtract 6 from 7 on the number line? Well, follow me and find out. I will jump 6 places to the left from 7 on the number line. We're left with 1. So, this shows that 7 minus 6 is 1. Isn't it fun? I hope you got the idea. It's time to move on to multiplication. We'll multiply 2 with 5. Multiplication is like faster addition. Look how I move 2 units at a time towards the right on the number line to get the product. Observe that I will make 5 such jumps. Don't you think I have made your task easier? See how quickly I could multiply 2 with 5 to get 10 as the product? That's it for now. You all have a great time doing additions, subtractions and multiplications on the number line. I'll go and catch up with Croak now. Bye!
Sona and Ishan are making necklaces using beads. They have used 20 red beads, 12 blue beads and 8 green beads so far. They are curious to know how many beads have they used in all. They both try to add the beads in their own way. Sona first adds 20 and 12, then add the sum with 8. Now it's Ishan's turn. He added 12 and 8 first, then their sum with 20. Will they both get the same answer? Sona gets 32 on adding 20 and 12. Then adding 8 to the sum, that is 32, she gets 40. Ishan gets 20 on adding 12 and 8. Then adding the sum 20 with 20, he gets 40. Yes, they get the same answer. Can you draw any conclusion about the addition of 3 whole numbers from this? This shows an interesting property of addition of whole numbers. We can see that 3 whole numbers can be grouped in any order to add them. Their sum will always remain the same. There are more such properties of operations on whole numbers. The properties of operations on whole numbers include closure property, commutative property, associative property, distributive property, and existence of additive and multiplicative identities. Let us explore closure and commutative property. Let us first discuss the closure property of operations on whole numbers. Consider 2 whole numbers, 12 and 9. The sum of 12 and 9 is 21. 21 is a whole number. Take another pair of numbers, 7 and 10. The sum of the whole numbers 7 and 10 is 17. Again, 17 is a whole number. Similarly, the sum of the whole numbers 0 and 15 is 15. And 15 too is a whole number. Thus, we can conclude that the sum of 2 whole numbers is always a whole number. In general, if A and B are 2 whole numbers, then their sum A plus B is always a whole number. This is called the closure property of the addition of whole numbers, and we say that the whole numbers are closed under addition. Are the whole numbers closed under subtraction also? Let us use the same pair of whole numbers to check whether the whole numbers are closed under subtraction. When we subtract 9 from 12, we get 3. 3 is a whole number. But when we try to subtract 10 from 7, the answer is -3, which is not a whole number. Thus, the difference of 2 whole numbers is not a whole number. If we try to subtract 15 from 0, the answer is -15. Again, the difference of 2 whole numbers is not a whole number. In general, if A and B are 2 whole numbers, then their difference A minus B is not always a whole number. So we can conclude that the whole numbers are not closed under subtraction. Next, let us proceed to see if the whole numbers are closed under multiplication. Multiplying 9 and 12, we get 108. 108 is a whole number. The product of 10 and 7 is 70, which is again a whole number. Similarly, the product of 15 and 0 is 0. And 0 is a whole number. In general, if A and B are 2 whole numbers, then their product A times B is always a whole number. This is called the closure property of the multiplication of whole numbers. Thus, we can say that the whole numbers are closed under multiplication. Finally, let us determine whether the whole numbers are closed under division or not. If we divide 12 by 9, we get about 1.33. 1.33 is not a whole number. Dividing 7 by 10, we get 0.7, which is not a whole number. When we divide 0 by 15, we get 0. We can see that 0 is a whole number. In general, if A and B are not two whole numbers, then their quotient A divided by B is not always a whole number. Thus, we can say that the whole numbers are not closed under division. Hence, whole numbers are closed under addition and multiplication, but not under subtraction and division. Now let us look at the commutative property of operations on whole numbers. Consider two whole numbers, 24 and 6. When we add 24 to 6, we get 30. Now let's change the order of the number as 6 and 24. Then add 6 and 24. We can see that still the answer is 30. Thus, we get the same sum even if we change the order of the numbers. Similarly, for the whole numbers 0 and 7, 0 plus 7 is 7 and 7 plus 0 is also 7. So, do you think we can draw some conclusion about the order of adding two whole numbers? Yes, we can conclude that the sum of the two whole numbers remains the same, irrespective of the order in which they are added. In general, if A and B are two whole numbers, then their sum A plus B is always equal to B plus A. This is known as the commutative property of the addition of the whole numbers. So, we can say that the whole numbers are commutative under addition. Are the whole numbers commutative under subtraction also? Let us find out. When we subtract 6 from 24, we get 18. Now, if we change the order of the number and subtract 24 from 6, the answer is negative 18. Similarly, for the whole numbers 0 and 7, we can see that when 7 is subtracted from 0, the answer is negative 7. But when 0 is subtracted from 7, the result is 7. From the table, we can conclude that the difference of two whole numbers does not remain the same if we change the order in which they are subtracted. In general, if A and B are two distinct whole numbers, then their difference, A minus B, is not equal to B minus A. So, the whole numbers are not commutative under subtraction. Now let us try to find out whether the whole numbers are commutative under multiplication. When we multiply 24 by 6, the product is 144. Now change the order of the number, that is 6 and 24. Multiply 6 by 24, we still get 144. Thus, if we change the order of the two numbers, their product is the same. Similarly, for the whole numbers 0 and 7, we see that 0 times 7 is 0 and 7 times 0 is also 0. Thus, we get the same product even if we change the order of the numbers. From this, we can conclude that The product of the two whole numbers remains the same, irrespective of the order in which they are multiplied. In general, if A and B are two whole numbers, then their product A times B is always equal to B times A. This is known as the commutative property of the multiplication of the whole numbers.